Let's think about coming up with a derivative rule for multiplication. So let's assume that we have two functions that are differentiable, f of x and g of x, and we want to come up with some formula for the derivative of their product. As usual, until we have such a derivative rule, the best that we can do is just use the limit definition of a derivative. So this is going to be the limit as h goes to 0 of the product function evaluated at x plus h minus the product function evaluated at x all over h. And when I say the product function, what that really means is, so the product function evaluated at x plus h, that's f of x plus h times g of x plus h. And then same thing for f times g at x, that's f of x times g of x all over h. All right, well, at this point, I mean, it's kind of hard to know what to do. I mean, based on our experience with the sum rule, finding a derivative rule for sums, we sort of expect possibly f prime of x and g prime of x to show up somehow. But you know, to get these things to show up, we're going to have to end up with, to get f prime to show up, we should have f of x plus h minus f of x showing up somewhere. And to get g prime to show up, we would have to have g of x plus h minus g of x showing up somewhere. But we just don't have those pieces, right? We have, everything is multiplied by something else, so it's hard to know how to get these pieces on their own. So it's not really clear how to proceed. One thing you can do if you have some problem and you get stuck is you can reason about the problem informally just to try to get some idea of what the answer might be. If you have some idea of what the answer is, then it can be easier to prove that that is correct, rather than just trying to reason your way to an answer without knowing where you're headed, right? It's a little easier to find the right path if you know where you're headed than if you don't. So what we could do is try to come up with some geometric way of thinking about a product. To do that, we need to come up with some geometric quantity that is a product. And one obvious candidate is area, right? If we have a rectangle, then the area of a rectangle is just the height times the width. So the area of this rectangle is f of x times g of x. And just for now, I'm going to stop writing the of x. So I'll have to keep in mind that everything is actually a function of x. Now, when we change x a little bit, this causes a change in f and a change in g, right? So maybe f gets a little bit bigger, and g also gets a little bit bigger. So maybe I should have put this label over here. G also gets a little bit bigger. And this causes a change in the resulting area. So to get some idea of what the derivative of a product is, we should figure out what is the rate of change of the area as we change x. Well, the rate of change of the area is just going to be the change in the area divided by the change in x. So let's figure out what is the change in area. Then we can just divide by the change in x. So for the change in area, this solid black rectangle, this is the area we started with, and so the change in area is going to be this extra stuff we get along the top and along the right hand side as delta f and delta, or as g and f expand, adding these extra bits, delta g and delta f. So how big is this change in area? Well, this change in area is kind of made up of three pieces. There is this piece along the top, and the width of this piece is f, or f of x, and the height of this piece is delta g. The piece along, so the area of this top piece is f times delta g. Now for this piece along the right-hand side, its width is delta f, and its height is g, so delta f times g is the area of this piece along the right. And this upper right-hand corner, that's delta f wide and delta g tall. So adding these three extra pieces together, the change in area is delta f times g plus f times delta g plus delta f times delta g. All right, now remember we were thinking about getting a rate of change, so we should divide by the change in x. So divide everything by delta x. And on the left-hand side, we get delta a over delta x. On the right-hand side, we get, let's see, delta f over delta x times g. So this delta x is going to end up under each of these terms separately, and it kind of makes sense to arrange the fractions so that all our deltas are in ratios like this. So we could write this term delta f times g over delta x, but it kind of makes sense to put the parts with the deltas together. So there's our first term, plus f times delta g over delta x, plus, and then for this last term, I'm not quite sure how to write this. Maybe delta f times delta g over delta x. Now our idea is that if we take a limit as delta x goes to 0, then on the left-hand side, this should turn into just a derivative, so dA dx. And then on the right-hand side, these ratios with deltas should turn into derivatives as well. So delta f over delta x, that's going to be df dx times g plus f times, and then delta g over delta x, that should be dg dx. And then, well, this piece with delta f times delta g, it's not so clear what's going to happen to this piece. If delta x is going to 0, then this piece here, delta f over delta x, this should be going to df dx, I guess. And delta g, well, if delta x is going to 0, delta g is also going to 0. So maybe this should be 0 here, in which case this last term just disappears. So just based on this geometric model of multiplication, it kind of seems like this is what we should be heading for a derivative rule for products. So df dx times g plus f times dg dx. So now that we think we know where we're headed, right? We have some guess of what the product rule ought to be. We can use this guess to sort of work backwards and fill in the gaps in our limit calculation. So, right, this delta f delta x is really coming from a limit, which would look like f of x plus h minus f of x over h. And that's all times g. And then over in the other term, it's f times, I guess this would be g of x. And then f of x times g of x plus h minus g of x over h. So you can see when we remember, we're working backwards, so probably where this came from is from factoring something out. So if we reverse that and multiply this through, you can see we're getting some f times g's. And in particular, we're getting an f of x plus h times a g of x, right? So that's a piece that that we should expect to appear when we do our limit calculation. So let's go back to our limit calculation. Right, remember, so the piece that we're expecting is f of x plus h times g of x. So if we go back to our limit calculation, right, this is the part where we got stuck right here. There is the piece that we were expecting, but that we don't see, is f of x plus h times g of x. Right? We want that piece to appear because that's a necessary piece to make f prime show up. Well, we can make this appear if we want to, right? One of the nice things about doing algebra is if there's a term that you want, you can have it, as long as you're willing to pay the price. And the price that we need to pay to have this f of x plus h times g of x, the price that we have to pay is, if we added it, we also have to subtract it, right? We have to keep things balanced because we don't want to change what our expression is, we just want to change how it looks. So minus f of x times g of x. Okay, all over h. It's hard to know at the beginning if this is the right thing to do, but at least it's producing this piece that we think we need. All right, so now that we have this written down, though, I notice that in this first piece, actually, so we have some options now, because this first piece has an f of x plus h. There's also an f of x plus h here and here. Right, so we might group some of these terms and factor out that x plus h. But there's also a g of x here, a g of x here, and a g of x here. So we might group some of these terms and factor out the g of x. Well, remember, what we're ultimately trying to arrange to have happen is for these differences to show up, f of x plus h minus f of x, and g of x plus h minus g of x. Well, here's a g of x plus h, and here's a g of x, and they both have f of x plus h. But if we grouped these two terms, there'd be a plus, and we want a minus, right? So let's take this term, f of x plus h times g of x plus h, group it with this term, minus f of x plus h times g of x, and then these other two terms, we'll put them together as well. So plus f of x plus h times g of x minus f of x g of x. And this is all over h, and we're taking a limit as h goes to 0. Okay, now these first two terms, they have an f of x plus h in common. So let's factor that out. So f of x plus h times, and then the stuff left over is g of x plus h minus g of x, and that's over h, plus, and then we can take the limit as h goes to 0 of the second piece, but these have a g of x in common. So we'll write our fraction first and the g of x over here, and when we factor out that g of x, the stuff left over is f of x plus h minus f of x over h. All right, now things are starting to look good because these things are starting to look like they're going to turn into derivatives. So we need to find the limit of this big product, but we can use the product rule for limits. So this is the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of g of x plus h minus g of x all over h, plus, and then we can use the product rule for limits for the second piece as well. we get the limit as h goes to 0 of f of x plus h minus f of x over h times the limit as h goes to 0 of g of x. All right, now we're almost there. We just need to evaluate each of these limits individually. This first one, as h goes to 0, I mean, it's tempting just to plug in h equals 0, but how do we know we can do that? I mean, what is it that justifies just plugging in the number, right? It's not always the case that to evaluate a limit you can just plug in the value. It's only when the function is continuous that you can plug in the value. So I guess the question is f continuous at x? Well, remember, we assumed at the very beginning that f is differentiable at x. Because if f doesn't have a derivative, then probably there's no point in trying to come up with a product rule for the derivative involving f. So we assumed that f is differentiable, but we know that if a function is differentiable at an x value, it has to be continuous at that x value as well. So the answer to this question, is f continuous at x, is yes, because it's differentiable. It has to be continuous as well. So we can just plug in the 0 and we get f of x. All right, times this limit, but this is just the derivative of g at x plus, now this limit here, that's f prime, the derivative of f at x, and then the limit of g of x as h goes to 0, well, there's no h in here, so it acts like a constant, so we just get g of x. All right, so what we got is that the derivative of f times g is, I'm actually going to put these in the other order, f prime of x times g of x plus f of x times g prime of x. And this is exactly what we thought it was going to be based on our geometric reasoning. So it's nice to see that geometric reasoning, even though it's not a proof, it does guide us to the right result. If we wanted to write this in Leibniz notation, it would look like this. So the derivative with respect to x of f times g is the derivative of f with respect to f times g plus f of x times the derivative of g. All right, notice that this is probably not what you would have guessed. So usually, I think if you had, at the very beginning, before we thought about areas of rectangles or anything else, if I had asked you to guess what the derivative of a product is, you might have guessed, well, maybe it's the derivative of the first one times the derivative of the second one. But that is not what we got. So this is not right. It's tempting to think so, but it's false. We can see that it has to be false because if we take the derivative of x squared, we can use the product rule. We know it's 2x. But another way to think about x squared is that it's x times x, right? So if we used this false product rule here, and we guessed that it should be the derivative of the first piece times the derivative of the second piece, well, the derivative of x with respect to x is 1, and then the derivative of this x with respect to x is 1. So we just get 1, but that's not what we were supposed to get. So, this shows that this tempting guess for the product rule is not the correct thing. The product rule is actually a more complicated phenomenon. I think this is really the first time this has happened, right? All of our limit rules basically were what you would have guessed them to be. And for derivatives, the constant multiple rule and the sum and the difference rules for derivatives come out to be what you would guess they would be. But for the product rule, it's very different. So be careful with the product rule. Incidentally, if we use the correct product rule to find the derivative of x times x, we ought to get 2x, like we got with the power rule. So if we used the correct derivative, or the correct product rule, we should get the derivative of the first thing, which is x, times the second one, which is x, plus the first one with no derivative times the second one with the derivative, like this. And then the derivative of x with respect to x is 1 times x plus x times this derivative of x with respect to x is also 1. So we get x plus x, and that's 2x. So you can see the correct product rule reproduces the correct power rule. The false product rule gives you nonsense. So don't use the false product rule, I guess.